In our last video, we looked at an introduction to the circle geometry at grade 11 level. Now we are going to build on that, and we are going to start looking at tangents to a circle. So a tangent is a line that is drawn that touches a circle at just one spot. Okay, and the first theorem that we are learning that involves a tangent is this one here. The tangent to a circle is perpendicular to the radius or diameter of the circle at the point of contact. So what does that mean? Why is that important to me? It's because this angle then is a 90-degree angle. Okay, so we can say there angle B2 is equal to 90 degrees, and the reason is tan perp radius. Okay, if I was given the diameter, I would have written tan perp diameter. Okay, and you may also use this perpendicular sign. You don't have to write out that word perp or perpendicular. Okay, so tan perp radius happens when they tell us that we've got a tangent and they tell us we've got a line from the center. But alternatively, if we have a line from a center that hits a random line outside of our circle at 90 degrees, then we've got the converse. So if we are given that B2 equals 90 degrees, then we can say ABC is a tangent. Okay, so this is the converse, tan perp radius. Okay, very important to know both of them, very important to be able to apply them in both directions. Okay, and again, you have a look at what you were given. If you were given a tangent, then you can deduce that the angle is 90. If you were given the 90, then you can deduce that the line is a tangent, converse tan perp radius. Okay, next up, two tangents drawn to a circle from the same point outside the circle are equal in length. So here we have two tangents. They are both originating here at point C. So there CA hits my circle at A, CB hits the circle at B. And so what we may then deduce is that this and this is equal. Okay, and why is that important to me? Well, because there's something very significant about the angles opposite equal sides. Okay, so if I was given something like this, I could then say, well, AC is equal to BC, and the reason is tans from same point. And therefore, because those are equal, we can say, therefore, A2 equals B2 equals the 70 degrees that they've given there. And that is angles opposite equal sides. Very important to always give a reason. Okay, so always try to keep a lookout for this one. Whenever they tell you you've got more than one tangent, try and check and see, do any of them originate from the same point? Because that brings with it some useful information that we could possibly use to solve some of the questions that will come later on. Okay, tangents from same point. Okay, the next one says, the angle between the tangent to a circle and a chord drawn from the point of contact is equal to the angle in the alternate segment. Okay, this one I really like. I find it so helpful in solving geometry questions and riders. Okay, so this is an angle here formed between the tangent and the chord drawn from the point of contact. Okay, so there's the point of contact of the tangent and the circle. Then here's a chord drawn from that point. So this angle is equal to the angle in the alternate segment. What does that mean? Well, it simply means that if I follow the starting points, so here and here, that's where the chord creates two starting points for me. That forms another angle here, which is called the angle in the alternate segment. Okay, and those two are equal. So this 55 and that angle there are equal. Okay, so I can say angle E is equal to angle B3 is equal to 55 degrees, and the reason there is simply tan chord theorem. Right, if they gave me the opposite, for example, if they said, well, this angle here is 55 degrees, and that one there is 55 degrees that we can see, then we can conclude, well, therefore, this line is a tangent. So that's the converse. If they give us the equal angles, we can deduce that there's a tangent. If they give us a tangent, we can use the tan chord theorem to determine the angles. Okay, so let's pretend that they gave us here that angle E equals angle B3 equals 55 degrees. Therefore, ABC is a tangent. That's only if they asked us to prove that. And the reason would be the converse tan chord theorem. Let's take a look at all of this knowledge and combine it in an example. Okay, so a circle with center O is given below. UTS is a tangent to the circle at T. So there we go, there's our point of contact. And they are giving us a bit more information here. BC is equal to CT. Determine with reasons the size of, let's see, angle CAT. Okay, so what we want here is this angle. Let's have a look at the information we've got. We have got an angle, and I always like to check where's the chord that subtends that angle. It's there. Okay, and now if you have a look with me, there's a tangent forming an angle between the tangent and the chord, and then there, if we follow up those two starting points of the line, we'll see there's another angle. So this angle and this angle are equal. Okay, so number one, we can say angle CAT is equal to 35 degrees, and the reason there is tan chord theorem. Okay. Second, they want us to find angle BAC. So BAC. Let's quickly fill in what we just worked out. CAT was 35. And then BAC. Now, what I try and do is I try and see, there's an angle at the circumference. Possibly, can I get this angle at the center? Okay, but I don't have enough information for that yet because I don't know that angle. Or any of these, because I might want to use radii. Okay, what I haven't used, this is always where I go to when my checklist runs out, is I go back to the question and I say, what haven't I used yet? And I haven't used the fact that BC equals CT. And so if I look at CT, I've got the angle there that's subtended by that chord. Okay, and if I look at BC, then this angle that I want is subtended by that chord. And so this is a bit of an alternative to the angles in the same segment theorem. So although it's not drawn like a little bow tie, I am allowed to deduce that this one here also equals 35 degrees. Okay, so number two, BAC equals 35 degrees, and the reason there is equal chords equal angles. Okay, so just one to get used to. We get used to the bow tie, but on the odd occasion they'll do it like this, where we've got a chord that equals a chord, and we've got angle all the way at the circumference there, all the way at the circumference there. So then we'll go equal chords, equal angles. That's our reason there. Okay, now they want BOC. So let's follow and figure out which angle that is. BOC. Okay, so there we go. It's the angle at the center. So earlier I was hoping to have this angle because I knew it would be double that one. But it's okay because now I've figured out this angle at the circumference, and so I can just build in a back to front manner. So I can say this angle O is going to be double that angle A. Okay, so let's do that. Number three, angle BOC is equal to 2 times angle BAC. The reason, angle at center equals 2 times angle on circumference. Okay, and so therefore angle BOC is 2 times 35 degrees, which is 70 degrees. So we can pop that in there. Okay, now we want angle OAC. where's my pointer? OCB. OCB. We want this angle here. Okay. So what I'm hoping you notice is that because they gave us this center of the circle, that means I can draw a line there, draw a line there. Those are radii, and radii are equal. Okay, and what do we know about angles opposite equal sides? They are equal. So I'm going to call that x and that x. Okay, but we're going to need to set this out so we get all of our marks. So question 4, the first thing we're going to say is that OB is equal to OC. And the reason there, they are radii. Now we're going to say, therefore, angle, let's say OBC, OBC is equal to BCO. And the reason, angles opposite equal sides. Okay, and then, maybe I'm just going to say, I think your teacher, if your teacher can see your sketch, you don't have to say this, let it equal x, but let's do it. So let angle OBC equal BCO, ooh, that little hat must be there, BCO equal x, okay? And now what do we know about angles inside a circle? Inside a triangle. X plus 70 degrees equals 180 degrees. The reason there, interior angles of a triangle. Right, and now we'll solve. So 2x plus 70 equals 180 degrees. 2x is equal to, let's take that 70 across. So it's 180 minus 70, which is 110. And so x equals half of that, because we'll divide by 2. X equals 55 degrees. Okay, and so therefore OCB equals 55 degrees. Alright, so loads there, and they love to combine. So we used our tan chord, and then we needed to go from there to solve all kinds of other things. Okay, just a few hints. Please remember to look out for radii. That's one that people often forget, and they sit and they feel stuck on a question for a very long period of time. And then remember this other version of angles in the same segment. Equal chords, equal angles. Okay, so when you find that you've run out of options and you don't know what to do, go back and read the description again and see what haven't we used yet. We already used the tangent, okay? We hadn't technically used the fact that O was the center yet, but we hadn't used this, that BC was equal to CT. And so then that immediately springs into your mind that there is a helpful theorem there, that if you've got equal chords that subtend angles at the circumference, then those angles are equal. Okay, and then finally, when you get stuck with something like this, we need to find this angle here. I again could go back and say circle with center O, and what does that mean? That means that every line that comes from O out to my circumference must be equal to each other because they are radii. And then don't forget to write that down and show it as part of your solution.